Good morning. My name is Krishnendu Dasgupta. I'm from AXONVERTEK AI and TrialBridge. Today, I'm showing you G.A.M.E.R.S, graph agents with multimodal entities and reasoning schemas. It solves how you reason across a patient's complete clinical picture when the picture scans and spans across X-rays, lab values, clinical note, pathology slides, and prescription. So how did we come to build G.A.M.E.R.S? G.A.M.E.R.S is part of the initiative that we are building under TrialBridge, which is on the to understand clinical trials and to create better insights of clinical trials. What exactly is the problem? So let me frame the problem correctly. Clinical AI has four structural pillars as well as weaknesses, I would say. One is multimodal silos. When I say multimodal silos, it means a radiologist's chest X-ray and the lab panel from the same encounter. Like what we see in FHIR data, which is getting into the protocol for a patient, are processed by different models. No system links them entirely together at an entity level. And what happens when you have too much of data around? You start to lose context. For example, let's say when eGFR declines from 48 to 35 over 6 months across 4 encounter, typical, let's say, RAG or any kind of graph RAG retrieves nodes independently. It cannot compute that slope. And eGFR measures how well the kidneys filter blood, helping to detect and stage chronic kidney disease. So the loss of context happens when you have a patient or you have the data which is moving across and there are too much of encounters. Then the fourth problem comes as hallucination. Without ontology and crowding, the model fabricates ICD codes. We have seen that models try to understand that which ICD code it should map to, which particular code or which hierarchy it should map to. And that's one thing which creates a problem. It tries to invent drug interactions and even confuses the treatment plan. The flat retrieval process of clinical reasoning required a certain hop traversal, and simple cosine similarity or vector search similarity wouldn't do that. What exactly is the solution? The solution is G.A.M.E.R.S. You have graph to prove relationships are first-class citizens. You have agents, not completely autonomous, because you need human interventions and human checkpoints. The data is multimodal, and for that, we're going to use G.A.M.E.R 1.54b, which can read X-rays, CTs, MRI, pathology, and there are other pathology models which we are also using. There is a model called MedSignit, we are going to use that. There is a called DeepPath, we are going to use the deep pathology models as well. E stands for entities. Now, what are these entities? For this G.A.M.E.R.S, we are just going to demonstrate 37,000 ICD-11 nodes which are connected and 158 RX norm in graph, not prompt. And when I say RX norm, these are like all the details of a drug. R stands for reasoning, hybrid RAG with the graph hops as a differentiator. And we will see that in action. And last is S, which stands for schemas. Now, we all know that it's when you look into patient data, it's all about FHIR protocol. There are FHIR formatted data. There are different format of data. There's imaging data. Even the schemas there. So we have to think of something which is interoperable by design. So if you look into this, the bigger sense is onto the graph, is onto the multimodality part of it, and is also part of the reasoning side of it. Can a LLM reason today? Yes. Can an LLM reason based on entities or other pointers which is out there? Perhaps not very well. But what we need is something which can sit all of this together in a local environment, in a local compute where the data resides, and actually gives us a proper reasoned entities over here. How are we planning and what is the system architecture for G.A.M.E.R.S? We have 6 Docker containers, 1 GPU. That's the entire deployment. We're using G.A.M.E.R at a VRAM capacity of close to 9 GB. It fits onto a simple RTX or homegrown GPU. MedSignit, again, a model which sits on the CPU side of it. Neo4j stores the graph, and RAG fuses keyword, vector, and graph. We're also going to talk about an agent which is also built upon G.A.M.E.R.S, a drug watchdog and a cohort alert. The numbers, what we are going to see on the side, are basically real, but the data is completely synthetic. So we will be talking about 10 patients, 472 FHIR samples, 37,000 ICD nodes, 158 RX nodes, and more than 32,000 relationships. And there will be a medical image that we're looking into it. And again, all of this is happening in one single GPU. So how exactly the knowledge graph works on this particular thing? We are talking about FHIR. Now, there are certain nodes which is talking about the clinical facts. We have ICD-11, which has got around 37,000 entities with hierarchy. And when I say hierarchy, let's say essential hypertension, and it's under the circulatory disease. Vector search should not know it. It can learn about it. But if you look into, say, okay, essential hypertension, VA00, what chapter it is under, what indication of ICD is it under, it will not know. And a simple vector search will never able to do that. And that's where graphs are very important and very useful to implement or to gather knowledge into the reasoning side of it. RxNow, when we look into it, 158 concepts. Now, this is again a drug format view. And we can look into about the drug, we can know about the active ingredient, the dosage, and everything. For example, metformin, which has a Rx UIID of 86975, and it has an ingredient, and then it should have a dose form and a brand. Now, what we also want to understand when we talk about a drug or a relation to it, we want to see at an ingredient level interaction checking and mapping. And that should be enabled. Agents, these agents are dynamic. Every agent runs and creates graph nodes. Reasoning is in the graph and not in the log or not in the LLM. It can LLM. The reasons can be done by language models, but it should not be just language model. It has to have graph. And that's where these agents comes in. And when we say that it is a multimodal data, so then we need to also have multimodal embeddings to finally understand that how the entire data talks with each other. This is where we diverge a little bit from the typical clinical AI. Most systems, hardcore synthetic reports, right? Like let's say kidney 9.8 centimeter, but the actual ultrasound shows 9.34. That's fabrication. So we need, even if you are using a part of an image and you want to generate synthetic data of it on which this entire system can work, you need to have systems which can do it. In G.A.M.E.R.S, images exist first. We are using a pipeline of language models. We are using a pipeline of SIGLIP, MedSIGLIP, the G.A.M.E.R family, which looks into each image, read calipers, identify consolidation, and then it looks into different things, sees the sickle cell if it is there. If there is a histopathology slide, we look into it. The findings go into the file record, and then they are finally loaded into a new 4J database. And that's where the graph entities are holding not just relational entity between the text data or embeddings from text, it's also holding from images, also holding a graph relations. The data is evidence aligned, and the report matches images because it was generated from the image. So what exactly are we talking about when we say that there is a problem? For example, let's say there's a clinician and the clinician wants to know what is the problem in a certain person. Is there any problem with amentism? Let's say amentis is a patient. What normally happens over here is the first one is the keyword search. Normally, the first thing it's going to do is that the agent will go and look into whether the patient exists or not. Now, when we look into it, there is a dimensional vector similarity which can happen, but that's not the only thing. The graph expansion happens, traversal encounter, look into it, look into conditions, meds, images, the medication, treatment. The treatments are again by relationships, and these are all temporal lab trends. All evidence then gets assembled, and finally all this data come together, and then we process it with the reasoning vectors and with reasoning data, and we process it with G.A.M.E.R. We return a 7 evidence item tag from vector match to encounter normative aging and a treatment path. And that's why it's not actually a standard RAG. So when we say it about agents over here, so what agents are we talking about? So there are two kinds of agents that works out of G.A.M.E.R.S. One is a drug watchdog and a cohort alert. We'll be looking at an example of drug watchdog in a few minutes. What happens is it fires a new prescription. For example, there is a patient and the patient already has a lot of prescribed medicines. They are having certain diseases and they already are on certain treatment paths. But then a new medicine has to be given. At the same time, it is also important to make a decision whether the new medicine should be given to that person or not. So what could be done is, like, for example, can we have it? And if we are doing it, then what are the different steps that we can do? 7 graph-powered steps, retrieve medicines, conditions, temporal labs, check the ingredients from the drug, and then an assessment happens through the medical AI. But that's not the end of it. Even though there's an assessment which is coming with a reasoning, we want to put the human intervention back. And that's when we come up with an approval and a rejection request. So whatever be there, no reasoning agent can actually make a decision. It can create a path and it will always say that this is exactly where we need a human intervention, but the clinician can look into say that, yeah, this makes sense. Okay, I will approve, or okay, I will reject it. Every reasoning step is a graph node, and it also internally asks, Why it is flagged? Can we query the graph and we can get a full chain? And that's how the CentOS system will be working. The human in the loop is non-negotiable. We want human in the loop for any kind of agentic or AI task when it comes to healthcare. Core over here is vector store, a typical RAG. And when we look into it, when we say that white graph traverse, think of this. There is a drug interaction which is happening. The 4-hop traverse med, right? So we go to a drug name, it goes to RxNom, takes the drug name, takes the ingredients, sign similarity, doesn't traverse. The lab trends are again 3-hop. And that's where we look into 3 hops in temporal computation. Vectors, they return isolated values. When we talk about cohort safety, 5 hops reverse traversal, and vectors cannot reverse. You have to know that if it doesn't work, it can reverse traversal and see into it. And the best thing, and the most important thing, is the ontology. It's child of the hierarchy. The embeddings do not quote hierarchy. And that is where I think graph encode relationships. Vectors encode similarity, and both are different information types. The best thing is merge them both to get a better reason or better decision-making process. Every application is basically a graph traversal and a reasoning through a language or a multimodal model. We look into polypharmacy, which we look into trials, we look into longitudinal data, where there is comparing imaging across encounters, lab slopes, threshold detection, or we look into treatment mining, where it is basically by treated followed by cross cohorts. Explainability is basically on the chain of graph nodes. It's not just like if you ask a system to explain that why did you take this decision? What was the patient recovering or not? What happened to the patient in the last encounter? It should not be going back and just read. It should go back and see that where it has happened, how it has happened, what was impacted. And through that, it is not only traversing, and it is not only looking at the report, but also looking into the sequence of the reports or the sequence of activities. And all of that is sitting through a relationship. So it is basically what are we looking at and so on. Each app only possibly because of their existing graph structure, be it explainable decision support, be it a cohort discovery for clinical trials, or be it a treatment pathway on a drug discovery. We will look into a few demos after this. So this is again a synthetic data. It's not a real patient. Patient is not real. It's a synthetic data that we're looking at. Ahmed Hassan, patient number 8 with 67 years age, avid, very, very, very big smoker, 45 years, COPD, goal 3 identified with that. The graph encounters 5 encounters, 3 conditions, 5 medication. There are 2 images that we're looking at. There are some ICD-10 mapping and ICD-11 mapping, and the medications are being tagged with their RxNom, CUI, RxUI IDs. We look into evidence chain for that person over here, where we see that there's a chest X-ray. And when we look into chest X-ray, this is where the G.A.M.E.R.S or the model reads actual X-ray and then do an RLO consolidation. For example, in the labs, it will look into the WBC normalization, and it will try to see that whether there is a PROPAM attenuation resolution or is a link on that. It will check values like SpO2, what is the value of that person, whether it was up or down, and then based on it, it can see and do a reasoning part of it. The treatment, let's say it has had treatment or the entire reasoning chain or the entire concept says that it's a triple therapy treatment being provided. But then after that, what treatment could be given to the patient? So again, there is a reasoning point of it. Again, there is a decision to be made. On the agent demo, we are going to look into a real-time agent where we are going to ask for a particular patient, and we'll see whether when we look into and say that can we give this patient dapagliflozin 10 mg at a daily dosage. Now, this medicine, dapagliflozin, it's basically commonly branded as Farxiga, is an SGLT2 inhibitor used to treat type 2 diabetes, heart failure, chronic kidney disease by removing excess glucose through urine. Now, this medicine have been used in different kind of diseases, but then at the same time, it's also important to see that the one medicine can be used while the patient is treated through and by the medicine. Before we go to the demo, we want to say it again, everything that you're going to see is on-premise. There are 0 external APIs. It's all happening on one GPU machine, fully open source. It's completely open source stack, which completely is built upon it. Human in the loop is enforced at an architecture level, and no code path from the agent to the verification request without physician approval. So with that, let's go and present a little bit on the demo. So as you see over here, this is what G.A.M.E.R.S stands for. And this is exactly how it looks. Over here, you can see there are patients, Maria, and you can look into it, the timeline. Overview is giving us what are the essential hypertension the patient has been suffering. The conditions are specified over here. For example, essential hypertension, CKD stage 3, and then the person is also having type 2 M with hyperglycemia. There are medication, metformin, and other medications which are there. For essential hypertension, lisinopril 20 mg has been given as a treatment heat map. Again, all of this, what you see, is built completely at a synthetic level. The idea is to show that how we do informed decision making when we have different kind of data. So let's say that a daily life of a clinician, they look into, or a doctor, they look into a patient record and they want to see that, okay, what has the patient been through? Now, obviously, there are EHRs and EMRs out there, but let's say we have one centralized dashboard where we look into the timeline. And this timeline, if you look into it, it's ingested through the FHIR data, and the FHIR data is pushed into this record. But it's not just the FHIR data. There's an outpatient where it says that the first treatment or the first time the patient was administered was at an outpatient on 2nd of September 2024. There have been series of events or series of evidences that we look into and encounters with one of the emergency, and then so we have an outpatient again, which was the last outpatient over here, and there was an ultrasound of the kidney that was being done. Now, when we say ultrasound of the kidney, there have been some finding. What are we talking about over here? But before that, let's say that if we look into it, there we can see that now with declining, if the first thing, if you look into it, routine DM follow up. Now with declining renal function, which we want to see trending despite movement problem, discussed modification and importance of glucose monitoring. How this data can be viewed by a clinician. This is where we look into it, where we say that it's not just a FHIR record. We also look into that how the data could be fed into it. Over here, we are looking at text. Over here, we're looking at numeral values, which is over the time with different variability into it. And then we have image data. And this image data can be directly connected to you through a DICOM or whatever imaging tools that you have. But the idea is that one dashboard shows everything from that one patient. How does exactly this look? From our structure, we're looking at a graph. So Maria Santos has 3 conditions, has these medication, has 4 encounters as we look into, one of them being emergency, 3 outpatients, treatment graph conditions. Right now, this is the most recent treatment. And if you're looking at an image note, it also says that, okay, if there has been a pathology or radiology or any kind of imaging data has been portrayed from the patient or has been done for the patient, it will come over here. Over here we see for encounter again, these are just like stats for that particular patient. We have a chat, we'll come to it in a while. Then we have an agent, and then we have coding. The coding over here, what it is important to see is that the patient disease, as we said, like, these are ICD-10 and 11 coding. But if you look into it, it's not just ICD-11. We have a traversal problem of it, right? Essential hypertension. We're talking about chapter 11, what chapter 11 is, and what kind of category it is, hypertensive diseases. The same thing, if you look into one of these patient drug record, it not only looks into the name, it also finds out what ingredient are like the drug has and what kind of dosage form. For example, if the patient cannot take oral tablets, then obviously you cannot give this drug. If the patient is not at all allergic to, let's say, one of these ingredients, then obviously we cannot have that. But that information cannot be held by just one language model. That information is always held by deeper inside of connected data or graph networks, as we call. Over here, a quick thing is, like, we have an example of, for example, if say Foreman, I can look into it and it will give me out all the RxUI IDs where we say that how it can be used and how it can be administered. If I go over here and say diabetes, I can see that the different labels of diabetes in ICD chapter, which are here, which sometimes is useful for a clinician to make a decision when they go to and fro to it. And they have this, whether they're type 1, type 2, or everything. And at each of them, you can see that what category or chapter from the medical coding standpoint, what are they part of? So let's go chat and let's ask a quick question. Some latest encounter summary. Before we do that, let's go to the timeline and we say nephrology concert or progressive CKD, EGRF declining from 48 to 35. Now, if I look into it, is it so? Yeah, 48 to almost 35. It has declined. So that's the timeline. So let's go to the graph and do a quick chat and do a quick ask latest encounter summary. Now, while this is running, this is looking into searching the graph and trying to understand that what exactly Mario Santos' clinical data is containing. It's looking into the data, it's looking into the different connection of nodes, it's looking into different aspects of data points. If it is trying to find out that in that last encounter, what was happening, it will not just fetch the data, it is going to fetch a complete set of information and will also give out how exactly it found that information. So it will take a while to generate this. Here we are. So the latest encounter is from 1st of March 2025. And there's a summary which is over here. The most important part is it's not the summarization that we're looking into it. The most important part is the evidence part of it. It did a vector search, but then again, it also looked into the treatment paths, which we said. And then it did, within 5 steps, it did 7 hops. So if you look into it, the treatment path was there called encounter note. It was looked into it, encounter note again. And then the step 1, as I said, if you remember that we were doing it, right? Like the keyword search on clinical metrics or the notes, then the vector similarity, and then the graph context expansion. Over there are multiple hops going through. Treatment path reasoning, this is again a multiple hop. And then we have the counter response. So if you look into this actually says over here, this is something over there. Now, if I say, so I'm not going to ask that what medication, what it is. I'm just going to try it out, like in the live environment, and see that what exactly does the model returns. Now, it should return from the context of whether the patient is suffering from hypertensive disease, right? If it returns, then it should say that the patient is suffering from hypertension. If it doesn't return, it will just say. But at the same time, it will again create an evidence path for each of the query that we're looking at. So this is very important to see that how this exact structure comes in and says to us. A quick thing about understanding is, if you look into it, the summarization before the answer. So as we said, we are going to do a quick demo of G.A.M.E.R.S. What you're going to see over here is a list of patients, as we said, and then each of these patients, if you look into it, we have different patients over here, where they are defined with their conditions, their medication, their treatment, that what treatment are they are from. And each of these patients, they are having some encounters. It has been mentioned about the conditions of the medications or imaging of the reports that they are having. How do we get to know about all of this? Now think of this way, that a clinician comes into it, and they have to go to EMR or they look into an EMR. But think that if the centralized ecosystem which can be there, and that can be given out to the clinician for informed decision making, then how it will look like. Now when we say that we are looking at timeline, and in this timeline what we're looking is the data which is ingested from a particular file record. And if you look into it, these are all encounters. These are like outpatient, then again an emergency, there was an inpatient, then the outpatient, and there's an outpatient as well. Now over here you can see there's an ultrasound of kidney which has been done, and all of these are being attached to the encounter itself. Then there are lab values which are there, right? Like, for all the lab values which have been done over the time, that can be viewed. So this is a text data. This is a numerical data. Then comes the imaging side of it. And in this, if there is an image available, then it can come through. If not, it will not come through. Then, for example, let's take Mario. For Mario, we have these 3 conditions. And over there, if you're looking to Mario's timeline, we have an outpatient where it is out there. And then over the time, for example, the first encounter was done on 2nd of September 2024. And that was the first event, or let's say the encounter, it's an outpatient. And then over the time, there was another outpatient event, which is over there on the 1st of December for Mario. So Maria had all of these. In fact, she had one emergency. And then at the end, the last encounter that she had was basically an outpatient kind of a request. And in that, there's a nephrology consult with progressive CKD. There was an ultrasound of a kidney for, the imaging that we have just for one single image. Now, again, these are all of this that you're looking at is basically just complete synthetic data. So over here, if you look into image, the image says there's a certain finding which is out there, right? There's a graph over here. In this, we can look into it. Maria Santos has these 3 conditions, has taken this medication over the time, has these encounters, like 2 outpatients, 3 outpatients, 1 emergency kind of categories. The current treatment is for essential hypertension. And then if there is an image attached to Maria, it will also show that it's basically a right kidney ultrasound just out there. Let's quickly look into the chat side of it. So for the timing part of it, what I have done is I have quickly tried to run a particular query beforehand. But let's say while the query is running, if we say what is the latest encounter summary, over here, what we are looking at is not just a summary which is coming from the timeline of the file record. It's basically looking into all aspects of it. And if you look into it, the latest encounter was on 1st of March 2025. Like you see into it, it not only specifies the encounter, it also specifies like what has been the consultation about. The biggest thing is it's not just a summarization. There's an evidence that what it did. It went through a vector search, it did a treatment paths, look into the graph nodes, did encounter node, go through all of it. And if you look into it, it went through 7 hops through 5 different steps, starting from clinical nodes to graph context expansion to reasoning of treatment and final response generation. So all of this, when you look into it, these are certain aspect of it which comes into from a vector search part of it. Then we have an agent. So in agent, if I just say the person, let's say, can take statin daily. If I just say whether the person can take statin daily, I have already tried this thing on the agent history. So over here, the agent is trying to reason through different graph traversal, through lab checks, RxNorm, and then it's trying to find out whether statin can be prescribed by the patient or to the patient or not. But then again, if we say that whether it can be done or cannot be done, it's one of the most important things when it looks into it. Reasoning is not just through data. Reasoning is not just through relationship. Reasoning is through making sense of what is actually coming up. So once this particular agent returns, it takes some time to run this agent, to go through the graph, to check on the different lab data that we're looking at for each of the patient, try to compare it with real world understanding of it, and then come back and give us a reason structure of it. And then also look into drug interactions and finally give us or commit to the understanding from a perspective of a model. So it should come through for a while. It's taking a while. I think it will be done in another couple of minutes, or maybe a minute. Okay, let's see. There you go. So if you look into it, the agent looked into the step 1, the patient identified, the current medication retrieved, active condition retrieved, lab train analyzed, and everything. Now, human checkpoint created. Now, what it is giving is that there have been 2 risk flags. One of the warning is that the patient is already having a potassium level is more than that in electrolyte, and the G.A.M.E.R.S is more than that. In that condition, do you really want to give this, right? So it will say that the G.A.M.E.R.S say that we are not going to be available for this. Manual review is required and 2 risk flags have been identified. Now it's up to us, like a human, to really look into it and say that whether this makes sense or not, and I should approve this new medication or not. And let's say this thing, I reject it, and I say more evidence needed. So the moment I do that, it goes into the evidence side of it. I'll look into it. Last big point is on the coding point of it, where we look into a different standards of it, where you can, or the clinicians can look into different hierarchy. For example, if I go to it and say diabetes and do a search, it will just not only give me the name or the chapter code or the disease code, but it will also look into the category and the hierarchy of it, like whether it is on the different disease or what kind of chapter, what kind of category does it belong to, right? This is very important because this is how on the structure of reasoning, these levels, these paths are understood at a reasoning level. The same thing happened with the RxNorm part of it. So if I go ahead and say metformin and try to do a search, it will return all the RxUI IDs which are there. And if I look into this as well, and patient drug coding on the hierarchy side of it, it gives us an important information about the ingredients, and then from the dosage form and with the brands as well. So there are conditions where we look into whether we have ingredients, and then if there is a clinical decision to be made, and we say that, okay, there are decisions to be made, and a certain compound or a certain medication has to be given, it's not just what the medicine can do, but also at ingredient level, whether the ingredient can be allowed given what are the different clinical parameters or the lab parameters or the lab values that we are seeing. So it's more of an informed decision making that we see. So that pretty much wraps up on the part of what we are saying. These are the stats, but we also look into different stats. So I think like this is pretty much, this wraps up the demo as of now. So